Thank you. Thank you also to give me the opportunity of talking here in this nice institute. I will talk about this paper, joint work with Chung-Ming and Tad et al. And this is my last paper on arXiv, and the title is the same of the paper on arXiv. So I will start. Hey, I will start with. We start with a quick introduction. Okay, on smoothable varieties, but in the paper, we with the consideration of the single varieties, then we see where smoothable helps to get some real cscK metrics. Okay, so let X be a Q-Gorenstein variety. And by Q-Gorenstein, I mean variety, I mean a reduced variety. So normal analytic complex space. The canonical bundle is a Q-line bundle. The canonical device is a Q-line bundle. And I assume also the X is normal. Okay. And I also assume that with the KLT singularity, so it has mild singularity. And also, okay, the dimension X is n. Okay, and let me give immediately the definition singular metrics on this setting. So, definition. Let omega be a Keller form. We say that omega p is a singular. Yeah, sure.
I mean, I guess some people here may not be familiar with a Keller metric on a singular variety is, so
yeah,
you can take it to be the restriction.
Yeah, any Keller metric is locally given by restriction of a Keller metric ambient space. So a smooth form, a restriction of a smooth form on ambient space on some. So in the projective case, you can embed your variety on Pn and see locally as restriction on some smooth metric on Pn. Thanks. Yeah, but here we will see that this omega phi will not be a Keller in general. I mean, we say that it's a Keller, a singular cscK metric. Yeah, the notation is K here, just because of, as in the smooth case, it's a singular cscK metric in the smooth case. But as happened in the Fano case, in the singular Fano case, there was this work by Zerahi and Jadou. They define singular Keller-Einstein metrics on Fano varieties, and this metric actually may have some singularities, may not be the description of smooth metric on some local embedding. So this is okay. We will say give the definition. This is a singular cscK metric if first omega p is scalar on the regular part of X. And so this is a really smooth on the regular part. And second, P is some omega Poisson harmonic function bounded. In the case omega is integral class, this set of Poisson harmonic function may be thought as singular metric on line bundle. And it's bounded. This potential is bounded. Satisfies S bar omega phi to the n equal to n Ricci omega p wedge omega p n minus 1 on the regular part of X, where S bar is just n times first chunk out of X. Again, that's one. Omega d n. So we are requiring that this current, this omega t, is actually hler on the regular part, and moreover, it always a really csCK metric on the regular part, and the potential is globally bounded. So this is the definition, and this S bar is the average of the scalar curvature, topological. Yes, sure. This PSH, okay, this is locally, maybe I can define it. I can define, yeah. It's locally the set of omega Q-harmonic function called omega Q-subharmonic. So they are all U that are locally integrable, such that locally U locally is given by G plus P, G smooth. P is a Q-subharmonic, so locally is given as this sum. And moreover, omega plus I over 2 pi the bar. Yes, yeah, maybe. This is positive as current. Here was a bit fast. In the talk, I will use the notation omega phi to be omega plus I over 2 pi the bar p. And after it might happen that I will, if I will write this as DVC, because I'm used to writing this way, but okay. So you are requiring that this has some positivity. So if this U is smooth and this is strict, then you have a Kähler form.
This L1.
What? L1, a locally integrable function.
Right.
Yeah, this means really bounded. Yeah. What here? Yeah, we take or this does not make any difference to us. I mean, you can ask with respect to omega n to be finite, or you can ask with respect to omega prime. Does not make any difference. Better form and comparable in. Yeah. Thanks. Yeah. Okay.
Well, each omega p is that locally defined object?
Good question. Okay, here we don't require that is globally defined.
In general, I mean, I forget.
In general, you can define, you can make sense of this if the motion pair omega phi has some density with respect to the bag, and then
L1 plus
LP, for instance, if LP, so you can make sense of it. We will see later how to define it. Basically. Yeah, but here we are requiring just some hler, and then here is smooth.
What do you need to require to have scalar? Did you lack that condition?
Yeah, but this is some kind of okay. Some kind of compactness assumption. For instance, in the Q-Gorenstein case, it is necessary because you require really the, otherwise you cannot solve the motion pair. And here we need it, and I don't know if really it is necessary, but we need it because we pass to some kind of metric, and we need that it's really. We will see later. Yeah. Good question. Yes. Thanks.
You compare the notion of singular Q-Gorenstein.
Yeah.
But is Q-Gorenstein on the regular locus, and then there's beautiful. So it's obviously equivalent to some regularities.
Yeah, exactly. Because then in Q-Gorenstein you can really show that this is really yeah, it means that it's really in with minimum singularities if you want. If you don't require this at infinity, a priori you may have that C have some behavior along with the singularities. That does not, for instance, they have not total motion per mass, full motion per mass. Okay? So this is important. Yes. Okay, yeah, this. Okay, remark. Okay. First remark, if X is smooth, then this definition coincides with cscK metric. So you recover the genuine cscK metrics by some regularity property, and they solve the equation omega phi to the n equal to e to the f omega to the n, Laplace with respect to phi, so with respect to the metric omega phi of f equal to minus s bar plus the trace with respect to phi of Ricci omega. This is well known for the audience. Moreover, first uniqueness holds modulo the connected component of the identity of the automorphism group. And this was due to Berman-Bergson. And second, okay, the cscK equation is the hler Lagrangian equation of the Mabuchi function. I denoted by m omega. Okay, let me write and I will explain. Okay, so in the smooth case, you want to solve this equation, and you know the uniqueness is model this component. Moreover, you know that there is a functional called the Mabuchi functional, whose is the error Lagrange function associated with this equation. So the minimizers of this equation solve the cscK. And this by h omega, I denote the set of all u smooth, such that omega u is point. So the set of scalar potential with respect to omega. And so the problem is now to understand that when there exists a cscK metric on a given class, and this is connected to some conjecture. First, to give an analytic characterization of existence of cscK metric, and second, to give an algebra geometric characterization. So I want to.
I just ask about the if X is smooth, this gives you genuine cscK metric. So is that something that follows from the Chung-Ming stuff, or is that something other area?
Yeah, it's it follows from yes, Chung-Ming. Yeah, such. Thanks. I want to draw a big table. I hope this definition is clear enough for the moment. So, assume X smooth. I want to talk about the Jan's properness conjecture. and YPD, the Altan Donaldson conjecture. It is known that there exists some cscK metric. cscK metric. Okay, I fix a variety. I fix a class, a Keller form omega. It's known that there exists some cscK metric in this the cohomology class associated to omega. So in alpha, this implies the coercivity, some kind of properness property of the Mabuchi function that I'm going to define. So this function and whose minimizer are the cscK. So, and this is due to Darvash and Rubinstein and Berman, Darvash, Lu. Then we also have the reverse. Then this the breakthrough, recent breakthrough by Chen. Then we also have the coercivity of the Mabuchi is connected to an algebraic notion called K-stability. So we have this implies the uniform K-stability. And this is due to Johnson. And then the missing part on the Yao-Donaldson conjecture is to prove that uniform K-stability implies coercivity of the Mabuchi. Let me say that in the final setting, everything is known, also the reverse. One has the Yao-Donaldson conjecture solved. And in the singular setting, omega Keller form, our first theorem says that if X is mutable, then we have the recursivity of the Mabuchi. So we define a Mabuchi function in the singular setting, and we prove that the recursivity of the Mabuchi implies the existence of a singular cscK metric. Again, in the fun setting, everything is known. Then I would like to talk about openness. So let me say, oh, yes?
Setting, I guess people mostly use the Ting.
Yeah, that's the main, yeah. Yeah, but still the result is known because the coercivity of the Mabuchi is equivalent to the coercivity of the Ting. Yeah. Yeah, you're right. One big advantage of the funnel setting is that you can deal with a different functional that is more easy. It's more easy to deal with. Yeah. We don't know because the problem in the implication is that we are lacking. We know the existence of minimizer implies the coercivity of the Mabuchi, but the problem we don't know the minimizers are cscK, universal cscK. So we lack some result, and also we lack the uniqueness modulo of the automorphism group. But we know that existence of a unique minimizer implies the coercivity. That we know. I will see that in the as part of the talk. Yeah, we have a family and the general fiber. Essentially, the general fiber is smooth. We will see more in detail later.
So, equalizer to coercivity, this is basically just the Rubinstein, I mean,
Darvash-Rubinstein argument. Yes, exactly. That is the argument. Yeah, but we need to the convexity of the Mabuchi, something that we proved.
no, it's the issue that your metrics are not really globally defined.
What?
I mean, your definition of CST is a very local definition.
No, they are globally defined, but as a current. And it says,
The equation is not a global equation, so the equation on regular.
Yeah. Otherwise, you have to make sense of the Ricci, and then take, in some sense, it makes sense of the wedge product, take the non-pure product, and so on. So, yeah, you can make sense of it globally, but it's, must be a bit careful. Okay. Then I want to talk about the openness of what? Of the coercivity of the Mabuchi. I take under consideration the coercivity of the Mabuchi.
So sorry, what's the coercivity of Mabuchi bringing on smooth Kähler forms or some finite?
It is on the E1 actually. Yeah, in the singular, yeah. In the smooth case, they are equivalent. In the singular case, you must be a bit careful. I think they may be equivalent. Now I don't remember, but yeah. Openness of the coercivity of the Mabuchi algebra. So, I mean, okay. So you can ask the coercivity of the Mabuchi function in two ways. First, changing the cohomology class, or in families. So, in the Kähler cone, this was known by Lebrun and Simanka. Plus, I mean, Lebrun and Simanka worked with the cscK metric, but since you have this characterization, then you have openness of coercivity of Mabuchi. In families, you can ask in families. Happens in families. So for smooth family, again, this is the Lebrun-Simanka result. In the singular setting, we proved this openness. So this is our theorem 2. We are openness the coercivity, so we can move the class. Yes, always coercivity of the Mabuchi. And we also have theorem 3. We also have openness and coercivity in families. And this one? Not really, because the point is that they prove uniform case stability for filtration. It's open.
They have this paper,
Yeah. Yeah, this is, they proved what I want to say immediately after was exactly this, that there is a notion of uniform case stability for filtration. That implies the coercivity, but this arrow is unknown. So they prove that this notion is open in the Kähler cone.
They have this synthetic actually.
Okay, so, sorry.
I call it a synthetic approach to something where they prove open with results in some generality that's kind of
okay.
So for example, it applies to it gives a Lorentz microgroup in the smooth case, definitely they say, but using the Mabuchi functional. But I mean, it's quite general, so it could plausibly apply to
No, yeah. I mean, I think it may apply, but I don't know if they never take under consideration this Mabuchi function in a singular setting, because I think that they never. I mean, we define it. I don't know if they define it as well. I don't know.
So
the paper that the paper that I know that I wanted to mention is exactly the fact that they prove that this uniform case stability is open in the Kähler cone. But this is a priori is conjecturally equivalent to coercivity. And another thing that I want to say is that these points support evidence about the openness of case stability in a more general setting, in the Kähler cone and in families. It's known for the Fano setting that we have a family of Fanos, case stability. I mean, the automorphism group is discrete, then it's the case stability is open. So this support. Yeah, although this is actually it makes sense so just for that move this trick. Yes. Okay. And this is, of course, this is the first step towards the Yatan-Rotzan conjecture for the singular case. This was the introduction. Now, more in detail. So let me start with variation approach. So we define a Mabuchi functional, the space of scalar matrix is defined as the entropy part plus S bar energy part minus the twisted energy with respect to the G. Okay, it's good to answer the question by Ved. We can define this Ricci, a single setting. So fix H metric on MKX. We have Q-Gorenstein, so this is it is an M such that this is a line bundle. And let okay, we define the adaptive measure mu H as the measure that is given locally as the omega wedge omega bar omega H to the square, 1 over m. We take a local potential, and then we define this adaptive measure in this way. This was defined first of all by Buxon, Berman, Kedge, Zerai. And then in this way we can extend the notion of Ricci. We can define the Ricci of mu H of this measure as minus 1 over m DDC log of omega. This definition does not depend on the choice of the representative omega, and this gives you a global 114 that is coincide with the definition of Ricci in the smooth case. And essentially now we can take Ricci of omega. Moreover, the KT assumption gives that this measure mu H is given by a density F times omega to the n, where F is in some LP for t bigger than 1. Then we can define the Ricci omega as Ricci of mu H plus BDC log F. So the point is that any measure for measure that locally, if you take a measure that log is given as e to the minus f d the bar locally, then you can define the Ricci of mu as DDC of f. This is the idea, and this coincides with the Ricci in the smooth case. This is the idea. Okay. So we can make sense of this. We can make sense of this twisted energy. In the Mabuchi, okay, I'm not defining this. I'm just saying that this is the entropy. This is the leading term in the Mabuchi, while these are two energy that essentially we see that can be controlled in some way. Okay, what we proved is that this function is translational invariant, and moreover, it can be extended some way.
The third term should involve some wedge product of Ricci omega with omega p.
Yeah. Okay. Now here it's fine because p is most actually. You see, because we have Ricci omega wedge.
Right.
Yeah, with omega p to the n-1, something like that. Okay, now j wedge omega j. And this is fine because this is smooth and this is a 1-1 current, so you can make sense of it. In general, we can extend to a singular potential thanks to the non-pluripolar product. So what I want to do now, as in the smooth setting, what happens is that you need to embed your set of Kähler potential into a slightly bigger space, slightly bigger in some sense. Indeed, the set of Kähler potential has natural topology on it, and we expect one of these. You can see this space, this set. You can complete this set and get in this bigger set when adding some function, some Trusiani function that have some mild singularities. So you can just completing your metric space.
We go to finite energy.
Yes, this is finite energy. So what I want to say is that E1x is endowed. We give a topology of a strong topology. What does it mean? Strong topology. This can be seen as a metric topology. So E1 x omega some distance d is a complete metric space. It was due to Darvash, a single setting Darvash and Pinezza gauge. And this strong topology may also be seen as the quartz refinement of the weak topology. The weak topology is the natural topology, the natural L1 topology, then you put on this set of Trusiani function, such that the energy becomes continuous. You're putting a strong topology in such a way that this first term of the Mabuchi is continuous. And this strong topology is very natural for motion pair equations because it is connected to the continuity of the motion pair operator, and it is really very useful for topology. So as in the smooth setting, now that we completed the space, we can look at how this Mabuchi functional behaves at infinity, what are the properties of this Mabuchi functional, and in order to try to minimize it to get some csCK metric. Indeed, we also proved, as I would say, that the Mabuchi functional is convex along geodesics. The point is that this space admits geodesics, and what we proved that generalized what is known in the smooth setting, and that this Mabuchi is convex along geodesics. But we have to add that with the geodesic joining bounded potential. but it will be enough to prove our theorem. So the point is that we have two potentials. They may have some singularity because they may not be smooth. We connect by a geodesic, and the Mabuchi is convex. That's convex. Okay. Sure.
So the M you choose is this like a kind of a notion of like a smallest n making it this is a Q line model, so you multiply by
this one, this M. Yeah, I know, but it's
like,
if you take another M, I mean, you for a different metric on some other power, then you get a different adaptive issue. But this is, you must think of that as a smooth form on the first chain class of the variety. That is like representative network class. Yeah. Yeah, let me say what to this. We say that M omega is coercive, or M omega now is defined from the E1 space to where joint plus infinity is coercive if Mabuchi omega u is bigger than a constant. So if there exists A positive and B real number, such that Mabuchi is positive for any u that is normalized. So it is like this is the intersection of this space with sup of u equal to 0. So we normalize the functions. So this function is translation invariance. So we are asking some kind of growth of this functional at infinity. This is the notion of coercivity that is needed is equivalent to existence of CK in the smooth case, and is needed in our case to produce CK when the variety is smoothable. And then we want to understand how this notion behaves in families or in the Kerr. So the main results. So now we can be precise about the setup. We have chi be an n+1 dimensional Q-Gorenstein variety. We assume that we have a map from chi to the disk that is proper, oromorphic, surjective map, such that xt is scalar for any t. Third, we have an emission form, omega, on chi, on Kali x, sorry, Kali x, such that omega t, omega t to xt is scalar. And we also assume that x0 is normal with KLT singularity. Our feature, something like that. Yeah, some singularity. all the fiber may be singular in this setting, this general setting. Yeah, but this open notion, open condition, so close by they are Kelty, they are normal also. Okay. You can write the theorem 3 before more precisely. So the coercivity the threshold delta T, a sup of all A real such that the Mabuchi of omega T is bigger than A D minus B. Okay. For any U in xt omega T for some B. For any T, I'm considering the maximum A such that the Mabuchi is coercive with respect to A. So it's not this maximum may be not reached, so it's a supremum, and then you can note that if sigma T is bigger than 0, that means that the Mabuchi is coercive. So the coercivity threshold is lower semicontinuous. This is the first result. So in particular, if M0 is coercive, omega 0, sorry, then omega T is coercive for any T close to 0. This is the openness result. To make a comparison with the Fano setting, let me say that in the Fano setting, this resembles a result of Bloom-Liu, where they consider the delta invariant, and they show the delta invariant is lower semicontinuous in families of Fano varieties. Then with Chung-Ming panel, in another paper, we prove that the ding is satisfy this openness. The coercivity of the ding is open in families, and this is analogous for the cscK case.
Paper is in the Zariski topology.
So yeah, this is the Zariski topology, this is analytic topology, yes, sure. Yeah, but this is the connection version. Okay. Yeah. So the main ingredient, the new ingredient, is the convergence in families of omega Poisson function. So we have our family. We want to understand when a sequence of Poisson functions that belongs to different fibers converge to a Poisson function in the center fiber. We want to define this notion of convergence. So the idea is we consider outside the singularity. The idea is to pulling back functions on the center fiber, and then it requires some kind of weak convergence. The problem is that you cannot pull in back in genetic fibers, so you cannot take they are not baromorphic each other. So what happens is that locally, outside singularity, we require that you have this convergence. So let tk go into 0 and set xk, xtk, and omega k, omega tk. We say then tk converge, no, maybe tk in fk omega k, maybe sorry, two-term function of the fiber xk converge in families to phi0, which one function is center fiber. If for any data that is U0 compact open set in a regular part of X0, U a global open set in curly X minus the singular part of phi, and F such that we have a diagram so we are taking an open set in the center fiber, and locally is we can find that our open set behaves as a product. We have this in this commodity diagram. We ask it for any data like that, the sequence fk star of pk converge in L1 to phi0, in L1 of Q0. So really, it's a bit technical, but the idea is to pulling back functions at the center fiber requires some L1 convergence. You can show that this does not depend on the open set that you choose, and so this is a well-defined notion of convergence. And we can say it's converging family smoothly if this converge smoothly, or in other notion of convergence. And this was defined in a previous paper with Chung-Ming, and with that, we also defined the strong convergence.
Sorry, what is F?
Sorry, this is F, sorry. This is, I don't know, yeah. And then fk, you have x0, you have fk, the maps from u0 to uk. This is fk. You're pulling back. So this. Okay. Thanks. So the strong convergence, we say that pk converge to phi0 strongly if pk converge to phi0 in that notion, and the energy converge. As I said before, the strong topology is really a key ingredient in trying to understand, to characterize the existence of cscK metric. So it's important to have a stronger notion of convergence if you want to deal with the cscK metric. And this is the natural strong convergence. Okay. Oh, yeah. That I have more time, but okay. Now the three key ingredients are, the first of the strong compactness. Okay. we say that UK, we have UK in E1 x k omega k, such that the entropy is uniformly bounded. Then there exists a subsequence UKH such that UKH converge to some U0 strongly. This result is was a technical proof, long technical proof, and already for the smooth setting, it was proved in the paper of Berman, Buxom, Gage, Zeraye, Jadot, and it's really where the entropy. I mean, this space is huge, and you need some compactness to extract some limit and to have some cscK. So this is really one of this theorem in the paper is one essential point. The second, we have a Love semicontinuity of H. So maybe let me write that three. Maybe let me pass. We can prove that you are Love semicontinuity for the Mabuchi. So what does it mean? So if UK converge to U0 strongly, then the Mabuchi, then limit of K to infinity of Mabuchi is bigger or equal to the Mabuchi of U0. To prove this, we need to work a bit more, because we need to, the Mabuchi has three pieces, the entropy, and two pieces that are energies. The energy is continuous with spectral topology by definition, but the twisted energy is quite tricky because you have to deal with the Ricci omega, that is singular. So the idea was to change the reference metric, to instead consider this Mabuchi, to change with another Mabuchi with respect to another metric that is singular, but whose Ricci is smooth. It's known by Tian that if you change the reference metric in this Mabuchi with a Kähler metric, this Mabuchi is by a constant. The singular setting, we change the reference metric with a singular, with a current, whose Ricci is smooth. And we can prove that also the twisted energy in that case converge. And by this change of variable formula, we can prove also this lowest energy. So now, with this, we have the to prove the theorem, basically what one assumed by contradiction, we take A that is smaller than T delta 0, MK, M0. So if MK is not coercive with respect to A, then exists, so this is A smaller than A0 such that MK is not coercive. By contradiction, we can construct a sequence if there is no Lopez continuous. And for each MK, we can find a potential UK that destabilize this coercivity. And from this sequence, we can basically show that this sequence converges to plus infinity. So using the convexity, we can take fix a D. So we can construct these potentials such that the point is we can construct this potential such that VKD is less or equal than D times A by contradiction, and such that the distance of VK D 0 is equal to D. Then once that we have this, we know that the entropy is bounded. If the entropy is bounded, we can use the compactness argument to know that there exists a subsequence converge strongly. And thanks to the second point, we know that the limit for this bigger than M0 V0D, that by assumption, since it's coercive with respect to A0, is bigger than A0 times D, because it is distance of V0D, minus B0. So if we choose D big enough, we find a contradiction. That's the proof. The really sketchy proof, idea of the proof. And the last minute, like to state the theorem for smoothable. So the key point in this theorem was really to prove the compactness for given by the entropy, and to define and to work with this really this strong topology to try to understand this strong topology in families. And of course, one of the main ideas is to change Mabuchi with respect to a reference metric that is singular and but has some nice property with the Ricci. So in theorem 1, before, assume x omega of a disk is a smoothing. Q-Gorenstein smoothing. So we have the same setting of before, but we are asking also that the general fiber is smooth. So if M0, so here I mean also that, okay, maybe let me write it. The center fiber is normal, is a scared singularities. And it is normal. If M0 is coercive, then x0 omega 0 admits a singular csCK metric, which is also a minimizer of M0. Moreover, the potential csCK P, so this is clearly the potential such that omega T plus VDC csCK T is SCK. Well, the potentials converge to P0 to PCCK 0 strongly and smoothly in the family sense. So the idea for this theorem obviously is to using the theorem of openness coercivity to produce this csCK metric, and then one wants to get a priori estimates for this metric to then pass to the limit and have a strong convergence. And moreover, smoothly here means that in the convergence in families, you are requiring the potential outside singularities converging infinity, but smoothly. And here we use the main problem is that in the family setting, you cannot really, I mean, it's difficult to adapt the Chang-Chang because one of the problems is that the holomorphic bisectional curvature is not bounded. So it's really, you have to work a bit, and we adapted a recent result of Guo Fong, and where we replace, we have some control of the entropy and some control of the alpha invariant of the fibers. Sometimes we was screwed by Gage Dinetza Genantia. So replacing working so much we could prove L infinity estimates, and from that we can then prove Laplacian estimates and higher order estimates. But it was kind of tricky working families, adapting these Chung-Ming families. That's what I say. Wait, yeah, just in time. Yes.
So that theory like that the map is some kind of like analytic criteria. No, A is separately, where you can like find a singular case to take a
Yeah. You mean if you have a punch disk, you have a schematic outside the punch disk, and you want to produce a schematic? Now that's kind of reverse, I think. Because here you want to, yeah, one is reverse. Yeah. The point is this Mabuchi, the coercivity of the Mabuchi conjecturally is equivalent to existence CCK. So we work with this instead of existence CCK. But working with the Mabuchi, we prove openness. We prove that. And the smoothing, we can really justify our definition of Mabuchi on CCK mapping, really producing good CCK mapping and good convergence in a smoothing setting. What, sorry? On the single varieties, you mean? No. This really, as in the Q-Gorenstein case, what does it mean being Q-Gorenstein singular for Q-Fano? What does it mean being CCK? It usually means that you solve some equations that are come back to the smooth case, and has enough regularity outside, and also not too bad regularity close to a singular locus. Usually, don't expect to be smooth. You have some kind of boundness or something like that. Yeah.
So, same question, Mr. Grill. Does this imply that the values of criteria for separateness for large levels of scale?
Yeah, but you want to translate a bit. I don't want to make gaff. It means that if you have two.
Yeah, so can it happen? I mean, basically, Gabriel's question is boils down to can it happen that by cscK diverges strongly and smoothly similar cscK metrics on two different points? Or is that impossible?
Or two different varieties, really?
So that's basically what
I see. I don't know. Okay. Trivial answer is that, okay, if you can imagine this result, like extension of this result when you have atomorphism, and then if the atomorphism group does not jump, what to say, you imagine that you have two sequences compared to different CCK metric on the same variety. That's yeah, in the discrete atomorphism group, I don't know if you have this. Yeah.
So I guess like it's like a logical next step to try and see like CSK, singular CSK setting fits in with case Mabuchi.
Yeah, right. I don't know if we didn't check. I don't know if the works of because the thing that one can do is to resolve the singularities, getting some kind of coercivity or some Mabuchi functional on some big NF class, and then adapting the. I don't know if it is already in the paper of Buxom, Samodo Johnson. See this of this coercivity less due to some case stability for this big NF class and maybe semi-positive class, and then because they have something also for semi-positive classes probably. So I don't know if the coercivity of this Mabuchi already gives you some different case stability. We didn't check. We didn't. Yeah, that's a good question. Yes. This is the first step, but yeah.